Welcome to Cosmic Discoveries. Today we're diving into the mind-boggling world of string theory. This theory suggests that the fundamental building blocks of the universe are not point particles, but tiny, vibrating strings of energy. Imagine a universe where everything from the smallest particles to the largest galaxies is connected by an intricate web of vibrating strings. These strings can vibrate at different frequencies, and their vibrations determine the properties of particles. It sounds like something straight out of science fiction, but this is the essence of string theory, one of the most fascinating and complex ideas in modern physics. It aims to provide a unified description of all fundamental forces and particles. In the quest to understand the fundamental nature of our universe, physicists have developed groundbreaking theories like quantum mechanics and general relativity. Quantum mechanics explains the behavior of particles at the smallest scales, while general relativity describes the force of gravity and the structure of space-time. However, these two pillars of modern physics seem incompatible when describing the universe's most extreme environments, like black holes or the Big Bang. This inconsistency has puzzled scientists for decades. This is where string theory steps in, offering a potential solution to unify these seemingly contradictory ideas. By proposing that everything is made of tiny strings, it provides a framework that could reconcile quantum mechanics and general relativity, bringing us closer to a theory of everything. The seeds of string theory were sown in the 1960s, a time of great intellectual ferment in physics. Scientists were grappling with the strong nuclear force, one of the four fundamental forces of nature. Gabriele Veneziano, a young physicist at CERN, stumbled upon a mathematical formula that seemed to describe the strong force in a surprisingly elegant way. This formula, initially met with skepticism, would soon become a cornerstone of what we now know as string theory. Little did Veneziano know, his work would lay the groundwork for a new era in theoretical physics. This unexpected discovery sparked a wave of interest, leading to intense discussions and debates among physicists worldwide. Physicists soon realized that Veneziano's formula could be interpreted in a revolutionary way by imagining that the fundamental building blocks of the universe were not point-like particles, but tiny, one-dimensional strings. This radical idea opened up new possibilities and avenues of research, leading to the development of a theory that could potentially unify all fundamental forces of nature. The dawn of string theory marked the beginning of a profound shift in our understanding of the universe, and it continues to inspire and challenge physicists to this day, pushing the boundaries of what we know about the cosmos. Instead of imagining particles as tiny, zero-dimensional points, string theory proposes that everything in the universe is made up of these incredibly small, vibrating strings. These strings are far too small to be observed by even our most powerful microscopes. Yet, their vibrations hold the key to understanding the universe's deepest secrets. Just like a guitar string can produce different notes depending on how it vibrates, the different vibrations of these fundamental strings give rise to all the different particles and forces that we observe in nature. In string theory, the universe is a grand symphony, and the laws of physics are the harmonies played out on these cosmic strings. One of the most tantalizing aspects of string theory is its potential to unify the four fundamental forces of nature: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. These forces govern everything from the interactions of subatomic particles to the motion of galaxies. Currently, physicists have separate theories to describe each force, but string theory offers a single, elegant framework that could potentially explain them all. This unification of forces is a holy grail of modern physics, and string theory provides a compelling path towards achieving this ambitious goal. String theory comes with some mind-bending implications, one of which is the existence of extra spatial dimensions beyond the three we experience in our everyday lives. While this might sound like something out of a science fiction novel, these extra dimensions are a mathematical necessity within the framework of string theory. These extra dimensions are thought to be curled up and compactified to such small scales that they are currently undetectable by our instruments. However, their geometry and properties could hold the key to explaining some of the most fundamental constants of nature, such as the masses of elementary particles and the strength of the fundamental forces. While string theory offers an alluring vision of a unified and elegant universe, it is essential to remember that it remains a theoretical framework. This means that, unlike theories that have been confirmed through experiments and observations, string theory is still in the realm of mathematical conjecture. It paints a picture of a universe where all fundamental forces and particles are manifestations of tiny vibrating strings, but this picture is yet to be confirmed by empirical evidence. One of the main challenges facing string theory is the lack of experimental verification. In the world of physics, theories gain acceptance through rigorous testing and validation. However, the predictions made by string theory are incredibly difficult to test with current technology. The strings, if they exist, are far too small to be detected by any current or foreseeable technology. These strings are hypothesized to be on the order of the Planck length, which is about 10 circumflex 35 meters. This is many orders of magnitude smaller than the particles we can currently observe with our most advanced instruments. Another challenge is the immense mathematical complexity of the theory. The equations that describe string theory are not only difficult to solve, but also require a deep understanding of advanced mathematical concepts that are not yet fully developed. String theory requires sophisticated mathematical tools and concepts, making it a challenging field of study even for the most brilliant physicists. The theory often involves higher dimensional spaces and abstract algebraic structures that push the boundaries of current mathematical knowledge. Despite these obstacles, researchers are making progress in developing new mathematical techniques and exploring potential experimental signatures that could provide evidence for string theory. The journey is arduous, but the potential rewards, a deeper understanding of the universe and the unification of all fundamental forces, make it a pursuit worth undertaking. Despite the challenges, string theory continues to captivate the imaginations of physicists and ignite our curiosity about the universe. The potential payoff of unraveling the mysteries of string theory is enormous. It could revolutionize our understanding of the fundamental laws of nature, shed light on the origin and evolution of the universe, and perhaps even lead to technological advancements beyond our wildest dreams. The journey to explore and understand string theory is still in its early stages, but the insights gained along the way have already enriched our understanding of the cosmos and pushed the boundaries of theoretical physics. Thank you for joining us on this journey into the captivating world of string theory. We hope you found this exploration of the universe's tiniest building blocks to be as awe-inspiring as we do. Remember to like this video if you enjoyed it and subscribe to Cosmic Discoveries for more mind-blowing explorations of the universe.